In late July 2025, a wave of attention turned toward one of the rarest objects ever to cross our skies, the interstellar comet 3I Atlas.
We've got some fresh images of 3I Atlas.
3I Atlas.
3I Atlas.
3I Atlas.
Some of the world's most advanced observatories, including Hubble and the James Webb Space Telescope, had locked onto it, capturing data that hinted at something extraordinary. Its coma was swelling to immense proportions. Strange fluctuations in brightness were being reported, and amateur astronomers began to note a faint green glow around the nucleus. For a brief moment, the story of 3I Atlas seemed poised to capture the world's imagination. Then the stream of official updates slowed and soon after stopped entirely. NASA and its partners attributed the sudden pause to solar viewing constraints and instrument safety protocols. But for many observers, the silence felt striking. When earlier interstellar visitors such as Oumuamua and Borisov were discovered, the flow of data was fast and public, feeding excitement and debate. With 3I Atlas, the blackout left behind a vacuum, and into that vacuum rushed speculation about what had been seen, why nothing more was being released, and what questions still linger about this elusive comet from beyond the stars. On July 21st, the Hubble Space Telescope captured some of the sharpest images of 3I Atlas to date. Just over 2 weeks later, on August 7th, those images reached the public, showing a small nucleus only about 5.6 kilometers across, but surrounded by a vast dust plume stretching sunward. Meanwhile, the James Webb Space Telescope had taken its turn, pointing its near-spec instrument at the comet on August 6th. Expectations were high that Webb's unprecedented sensitivity would deliver breakthrough insights. But when details emerged, they came only as dry technical notes and cautious preliminary comments. No vivid headline images accompanied them, only suggestions that deeper analysis was underway. Later in August, Gemini South in Chile contributed its own set of images, confirming 3I Atlas's activity and tracking the evolution of its tail. Those data entered public archives in early September, sparking another wave of online discussions. Yet soon after, the pace faltered. Past September 22nd, there were no new flagship telescope releases. Hubble, Webb, Gemini all fell silent. For those following closely, the gap was glaring. The explanation lies in the unforgiving geometry of space. Observing with Hubble or Webb is not as simple as turning a telescope toward a bright point in the sky. Both observatories are governed by solar avoidance rules, strict limits designed to prevent stray sunlight from damaging their sensitive optics. For Hubble, the cutoff is 50 degrees from the sun's position. For Webb, the requirement is even stricter at 85 degrees. These values are hardwired into the observatory's planning tools. As 3I Atlas moved along its orbit, its solar elongation steadily shrank. By late August, the comet had crossed both thresholds. Hubble reached its limit shortly after July's images, while Webb managed its August 6th run just before the cutoff. Once 3I Atlas drifted inside those angles, the telescopes entered automatic blackout. Observing was no longer permitted, and no override was possible. Any attempt to schedule such an observation would trigger safing protocols that could shut down operations until a review. The silence was not deliberate secrecy, it was physics. That silence, however, coincided with tantalizing hints from the data already collected. Hubble's July images revealed a coma nearly 348,000 kilometers across, greater than a quarter of the sun's diameter. Such a scale is extraordinary, far larger than most comets at similar distances from the sun. Spectroscopic notes hinted at something stranger still, a possible dominance of carbon dioxide in the coma. If confirmed, this would be a profound clue about 3I Atlas's origins. Most comets within the solar system display water as their dominant volatile at this range. A CO2-rich composition could point to very different conditions in the comet's birth environment, far beyond our system. Though no peer-reviewed paper had confirmed this as of late September, the whispers lingered, and scientists did not deny the possibility. Ground-based observers quickly stepped into the void left by the silence of Hubble and Webb, and their efforts became the main thread of 3I Atlas's story. Night after night, telescopes in backyards, university observatories, and regional survey facilities tracked the comet's progress across the sky. What they saw was both familiar and puzzling. Reports consistently described a greenish tint spreading through the coma. This kind of glow is not unusual. Molecules such as dicarbon, C2, and cyanogen, Cn, often fluoresce green when excited by sunlight, and many comets display the effect. Yet in the case of 3I Atlas, the green seemed uniquely bright and oddly persistent, hanging on from observation to observation in a way that defied easy comparison with previous comets. Without spectra to confirm the chemistry, the exact cause remained uncertain, but the visual impression was striking enough to stir debate.
The comet's plume, first identified in Hubble's July images and later captured again by Gemini South, also became a point of fascination. Unlike the broad, steady tails of many comets, 3I Atlas's plume appeared changeable. On some nights, observers reported a sharp, well-defined sunward spike. On others, it looked diffuse, less distinct, or skewed to one side. The brightness also seemed to vary, occasionally flaring before fading back again. To some, these variations pointed to jets or outbursts on the nucleus, localized vents releasing gas and dust in sudden bursts. To others, the changes were nothing more than shifts in geometry, as Earth's viewing angle altered the appearance of dust streams. The lack of flagship data left no way to settle the argument, and so the plume became a mirror for competing interpretations. Photometric measurements added a further layer of complication. Observers around the world tried to track 3I Atlas's brightness, but their results often failed to align. Amateur astronomers using modest telescopes and CCD cameras posted estimates that sometimes differed from professional-grade observations by more than a full magnitude, a factor of more than 2 in brightness. Such discrepancies are common to some extent. Differences in calibration, sky conditions, and equipment can easily skew results. But the scatter for 3I Atlas seemed unusually large, and in some cases, even individual observers reported fluctuations from night to night that were difficult to explain away as simple error. The possibility emerged that the comet's brightness was genuinely unstable, flickering as activity surged and subsided on short timescales. As September gave way to October, the lack of new data began to feel personal for those who had invested time and passion in tracking the comet. Social media threads filled with frustration. "It's like chasing a ghost," one amateur astronomer wrote. "Every night we're guessing what's actually happening out there." Another demanded, "Why can't we just see the raw data? What are they waiting for?" The reality is less sinister, but no less frustrating. Every observation from Hubble and Webb enters a long calibration and review pipeline. Raw images are not instantly usable. They're riddled with cosmic ray strikes, detector quirks, and background noise. These must be carefully removed or corrected. For Webb, the process involves multiple stages, each checked and rechecked for errors. A single misstep could lead to claiming a chemical feature that does not exist. Beyond the technical steps lies policy. Hubble data generally carry a 6-month proprietary period. Webb's can extend to a year. Principal investigators who design the observing programs are given first access, a reward for winning the highly competitive time. Some choose to release data early, others wait until they're certain. And then there's institutional review. Every headline image or press release must pass through NASA, ESA, and sometimes CSA. The layers of approval can delay even non-controversial findings for weeks. For a high-profile interstellar object like 3I Atlas, the pressure to avoid mistakes is even greater. As one JWST scientist explained, "It's better to be right late than wrong fast. With interstellar targets, there's no second chance." Still, into the silence rumors spread. Some speculated that classified satellites had captured images too sensitive to release. Others suspected deliberate story management to prevent panic over a potential anomaly. A few believed the data were simply so strange that scientists were struggling to make sense of them. The modern media landscape only fueled the speculation. Bright, photogenic comets trend easily. 3I Atlas, with its scattered updates and blackout, slipped from attention. After Gemini's early September images, online engagement briefly spiked, only to drift toward conspiracy hashtags as the blackout stretched on. Behind the scenes, though, the reality remains steady. Every dataset grinding through a meticulous, multi-stage pipeline designed to catch errors and prevent premature claims. Compared to the open flood of data during Oumuamua's discovery or Borisov's steady cadence, 3I Atlas felt painfully slow. But the difference was not secrecy, it was a collision of technical constraints, proprietary policies, and multi-agency review. The next clear opportunity to observe 3I Atlas came not from Earth, but from Mars. On October 3rd, the comet swept past the red planet at a distance of just 0.19 AU, around 28 million kilometers. In cosmic terms, this was a remarkably close approach, though still far beyond the reach of detailed imaging. The event offered a rare chance for Mars-based spacecraft to step in, while Earth's flagship observatories remained locked out by solar geometry. The ExoMars Trace Gas Orbiter, equipped with the CASSI camera, and NASA's Mars Reconnaissance Orbiter, with its powerful HiRISE instrument, attempted to capture the flyby. Both instruments are legendary for their sharpness when it comes to Martian terrain. CASSI is celebrated for 5 meter per pixel detail of the surface, while HiRISE can resolve features down to about 34 centimeters per pixel in orbit around Mars. But at tens of millions of kilometers, those capabilities diminish dramatically. Each pixel suddenly stretched to cover hundreds of kilometers of space. The comet's nucleus, somewhere between 320 meters and 5.6 kilometers across, would appear as nothing more than a single unresolved dot, too small for even the best optics to tease apart.
This limitation meant that anyone hoping for crisp, close-up images of 3I Atlas from Mars was bound for disappointment. The instruments were never designed to track fast-moving deep space objects. Their exposure times had to be short to avoid smearing, and the signal-to-noise ratio dropped quickly as the faint comet streaked across the background stars. In essence, the Mars orbiters could not reveal structure in the coma or the tail. They could not show jets, plumes, or the shape of the nucleus. What they could provide, however, was still valuable: photometry. By measuring 3I Atlas's overall brightness from Mars' orbit, scientists could gain an independent check on the comet's activity. Such data are particularly critical when Earth-based telescopes, and especially the big flagships, are sidelined. A sudden brightening during the flyby might point to an outburst or fragmentation event. A steady light curve would suggest a more stable release of volatiles. Just as important, the Mars spacecraft could relay their observations quickly. Both the Trace Gas Orbiter and Mars Express have streamlined data pipelines, capable of downlinking and processing within 24 to 48 hours. In a period of silence from Earth's primary instruments, even a simple dot of light, if measured precisely, could break the information drought. With the Mars encounter behind it, 3I Atlas moved toward another critical moment: perihelion. On October 29 or 30, the comet would pass closest to the Sun at a distance of about 1.36 astronomical units. This was not close enough to make 3I Atlas a true sun grazer, but the encounter still promised to push the nucleus to its limits. Rapid heating, high velocity, and the stresses of solar radiation could destabilize the surface. Would 3I Atlas's nucleus hold together, or would it fracture under the strain? For observers, perihelion offered several key signatures to watch. The most obvious was the light curve. A smooth rise in brightness, followed by a gradual decline, would suggest a relatively steady release of gas and dust. Sharp, irregular spikes, on the other hand, could indicate surface outbursts or even fragmentation. A single jump in brightness would not be enough to claim a breakup. Patterns confirmed by multiple observers would be essential. Another expected marker was the behavior of the comet's anti-tail. This is the curious sunward-pointing spike of dust that can appear in wide-field images created by particles aligned with Earth's orbital plane. As Earth's perspective shifts, the anti-tail can flip, fade, or intensify. For 3I Atlas, models suggested the anti-tail would reach its most dramatic appearance near perihelion, only to diminish rapidly afterward as the geometry changed through November into December. Tracking its orientation across successive images would offer important confirmation of dust dynamics and orbital details. Color was also on the watch list. Amateurs had already reported a greenish hue in 3I Atlas's coma, likely due to molecules such as dicarbon or cyanogen fluorescing in sunlight. But if that green glow faded or shifted after perihelion, it might signal the depletion of certain ices or the exposure of fresh material from within the nucleus. Without spectra, though, images alone would not be able to prove what was changing. Only renewed access to Webb and Hubble could settle the question.
That access was expected to return in December. As 3I Atlas's elongation from the Sun widened, both flagship telescopes would be able to target it once more. The community anticipated a wave of new observations: high-resolution imaging from Hubble, spectroscopy from Webb, and a chance at last to verify whether carbon dioxide truly dominated its composition. These data could also resolve whether the brightness scatter reported earlier reflected real changes in the coma or simply inconsistencies in measurement. Looking still further ahead, orbital dynamics suggested another intriguing possibility. If 3I Atlas survived its solar passage intact, a favorable geometry near Jupiter in 2026 might provide another opportunity for study. The comet's journey was far from over, and its long arc through the solar system promised future windows for discovery. For now, though, the picture remained incomplete. What astronomers knew about 3I Atlas was striking. A coma hundreds of thousands of kilometers wide, a plume shifting unpredictably, hints of unusual chemistry, brightness measurements that refused to align, and a green tint that seemed brighter than in most comets. What they lacked was certainty. No peer-reviewed spectra had yet confirmed the suspected carbon dioxide dominance. No definitive explanation had accounted for the scatter and brightness data, and no consensus had been reached about the comet's shifting color. In the meantime, frustration and speculation filled the gap. Amateur astronomers posted nightly images, comparing notes across continents. Professionals urged patience, explaining that the blackout was not a choice, but a consequence of orbital mechanics and careful procedure. Yet the waiting felt like absence, and absence felt like secrecy. Between the hard limits of telescope design and the deliberate caution of the scientific process, the story of 3I Atlas became one of fragments and anticipation. It was a reminder that in astronomy, even in the age of instant information, some discoveries still unfold at their own pace. The case of 3I Atlas illustrates the tension between how science is practiced and how it is perceived. Scientists prioritize caution, careful analysis, and accuracy. The public, along with many amateur astronomers, crave immediacy and openness. Silence, even if built into the system, feels like secrecy. In that space between methodical progress and impatient curiosity, rumors thrive. But the real story is still unfolding. 3I Atlas has not finished its journey, and its true nature remains only partly revealed. As it swings past the Sun, re-emerges into view, and perhaps offers future opportunities near Jupiter, the world will finally see more of this enigmatic interstellar traveler. For now, all we can do is wait, watch, and wonder what secrets 3I Atlas still carries from the stars.